start again. It's a pleasure and the honor to introduce today's speaker in our colloquium, Professor Fedor Bogomolov from Courant Institute in New York. And before he worked in Russia, the Steklov Institute, and nowadays he's in New York. How I can describe Bogomolov's work? I would describe him as a ubiquitous mathematician, someone who started from topology, moving from algebraic geometry, studying classification of surfaces, introducing some theorem about desingularization of varieties, and let's say in the last part of operating from the beginning, working also in Diophantine problems, and with application to some to Anabelian theories. And yes, I speaking with you before, he said that his attitude was always starting something completely new. And when the problem was had too many followers, to change the subject. This is completely a different attitude than the usual Facebook way of doing, in which you need a lot of followers, and you are good if you have a lot of followers. In his attitude is to do completely different, and not just changing direction, but also going to really deep problems. Thank you very much.
Okay, thank you for the introduction. Okay, so mathematics, how to say, progress slow. The real mathematics progress happens slowly, as every progress. Real progress is slow movement. Past progress is not a progress, usually. So what I would like to talk about today is kind of connecting topology and geometry with arithmetics. Namely, I will be speaking about some properties of projective curves. So I will recall that for everybody who is familiar with it, I will say that the main object will be smooth, complex projective curves. So which is notation will be usually C or C with something. Yes, but on the other hand, the people who don't like or don't know algebraic geometry enough can think about as Riemann surfaces with additional structure. So just oriented Riemann surface with additional structure, which is complex structure, some structure, local, some special complex coordinates. Or all such surfaces, and usually it will be, so if genus of C is just the number of handles you need to glue a surface. If it is greater or equal to 2, then you can imagine it's the same as C is just a quotient of phase by gamma. This is two-dimensional disk, two-dimensional real two-dimensional complex disk, so Z less than 1, divided by gamma, where gamma is a subgroup in feature 2R. And depending on conjugacy class of this subgroup, you obtain different surfaces. So on the one hand, so this is purely complex object. This is complex object. But on the other hand, it actually is algebraic variety. I won't go too far in describing anything. The only thing we need to know is that in this case we have, so there are plenty of meromorphic functions, on C in this case, and then and in fact they constitute actually, and they constitute one-dimensional. And maybe algebraically, in order to think about it, you can think about sort of what is one-dimensional field over C. In this sense, over C is so this is the same as finite algebraic extension of C of T. Maybe this is complex numbers. So you take a standard field C of T, these are rational functions of one variable, take some finite degree extension, and that's your object. That's this field. And then in the case of curves, the theory of kind of algebraic geometry is perfect. There is a perfect theory. That means there is a one-to-one correspondence between one-dimensional field and curves. So everything is rigid. There's a standard uniformization, complex uniformization for all curves, and so on. Yeah? Okay. So I would be interested in more algebraic side of the problem. Maybe I'll remind that if G of C is equal to 1, this is just P1, only one curve. This is a projective, so this is topologically S2. And G of C is equal to 1 means C is equal to, let me say, E, because for such, this is elliptical. E. And in this case, E is is a group, and it is a quotient Z by Z. So all of them have a very nice, all these curves have a very nice analytic description. But as I said, I'm interested in algebraic description, algebraic properties, and in particular maps between curves. So any function. So first, notice that we are saying what is meromorphic function. It is, so we have a complete curve with local complex coordinates. So this Riemann surface is local complex coordinate. And then a meromorphic function is just a map C to P1, which is a map which is locally meromorphic, but this is given by one function. So F is inside of this field, let's say C. So these are maps from F to Z to a very particular curve. But we are interested, and I'm going to be interested in maps between different curves. So there are such maps. And in particular, among all maps, there are unramified fibers. So topologically, that means, so if you have C is H by gamma, then C prime, C tilde is unramified covering. It's finite. Unramified covering of C. If, in fact, if it is obtained as a quotient where gamma prime is gamma, subgroup of gamma, and then there is an H. So this is purely topological picture. You have a quotient by a group, by free acting group. Yes, so we assume gamma acts freely on H. Yes. And then if you take a subgroup of finite index, we have a map, we have a topological map, but it is also algebraic map. Algebraic in the following sense, that if you have such a map, let's say phi, then phi star of C. So the fields, meromorphic functions are moving up. So includes into C. Okay, So that's a particular class of maps, and in fact, many properties, many arithmetic properties now. That's when I'm coming to arithmetic properties. Many arithmetic properties of the curve C and its finite and ramified coverings are very similar. That was noticed already long ago in the 50s, that some kind of statement, that many statements about the properties of rational points here and here are equivalent. And therefore, now I have to come to a kind of notion of arithmetic curve. So arithmetic in the following sense, in a very simple sense. You see, when I'm saying about field of complex algebraic, I put here C. So these are complex neuromorphic functions. However, we can consider in a similar way inside the field C, the field C contains a subfield, the subfield of rational numbers and C is algebraically closed. C is algebraically closed to all polynomials with coefficients in C have solution in C, and therefore it contains also what is called algebraic closure. C contains Q bar, algebraic closure. Okay. So that's what. So these are also. This is a field of algebraic. Field of algebraic. So these are complex numbers which satisfy polynomial equation, irreducible polynomial equations over Q, over rational coefficients. So there is a polynomial with rational coefficients, which is it. Okay. So now that's what we can say. So this is about C. Now this is kind of zero-dimensional case. So see, it is like a complex. Now what about dimension 1? So one-dimensional fields. So among one-dimensional fields, so complexes, finite extensions of C of T, there are extensions, okay, maybe I'll start arranging here. So among all L extensions, so finite extensions of C of T, yes, there are extensions which are obtained in the following way. Extensions L prime, L, which are obtained from finite extensions of Q bar. So we take Q bar of T and then embed it into, take L prime, which is kind of, so this is just dimension, so the field which is obtained as a finite extension Q bar of T, and then kind of tensor it with, I wouldn't say exactly tensor, but just it's sort of the same, so this is a vector, so we can think about L prime as a vector space over Q bar of T, but then you kind of tensorize this vector space with C, and we obtain L. Not every such extension here is like that. So in fact, what happens is that if you have, okay, I will always be talking mostly about genus greater than 1, so therefore I like to allude to this quotient here. So not all the fields are like that. In fact, if genus of C is equal to, is greater than, is equal, yes, if genus of C is greater or equal to 2, then all different curves of genus C, I mean complex projective curves, are parameterized by 6G minus 6 real dimensional variety, which is also has something which is also algebraic variety of 3 dimensions 2G minus. So here we count real variables, here it's like complex variables. So you can imagine that this is big variety, but moreover it's also arithmetic variety. So the parameterization space, and this is something which you may know, this is called moduli space, is arithmetic variety, moduli space. So this is kind of moduli space, so this is also algebraic variety over Q over rational number. So it has a structure of algebraic variety over rational number, and as in complex space, it contains points over Q bar, dense set of points over Q bar. And these points correspond to curves, arithmetic curves. So how to imagine this set? Just consider a simple case. Let's assume it is Cn. Yes, so Cn, which is a variety over C. This is what is called a affine variety over C. And then it contains, so inside here, we have Q bar n to the power n. So n coordinates, Cn has n coordinates, z1, zn, and inside this space there are points with coordinates which are algebraic numbers. These are arithmetic, so-called arithmetic points of C. And similarly, so this set is clearly dense in every possible sense inside Cn, and similarly for every algebraic variety like that one, moduli space, there will be dense set of points over Q bar. So we have, but Q bar is countable. What's the difference? Principal difference between Q bar and C is that Q bar is countable, but huge. Yes, everybody else. So everything can be approximated. Okay, so therefore we have this. So what I'm going to consider now, this particular variety. And the problem I'm going to discuss mostly for these varieties, but also mostly for these curves, but for some, okay, let's just mostly for this curve, is the following question, so-called dominance question. So now I'm coming to basic definition. So dominance. We say that C dominates C prime. So both are curves, and we assume just anything. So C dominates C prime if there is a finite unramified covering C tilde. So this is a finite map, so that means it's unramified covering with a finite map onto C, such that it subjects onto C prime. So anyway, if you look for generic curves, let's say complex curve, it happens very rarely. So usually every curve, the curve, so if C prime, certainly, if C prime is P1, everything dominates. So every curve dominates because it's just the existence already functions here. However, if we consider curves of if C prime has bigger genes, so not many geometrical, any curve C has only finite number, has at most finite number of maps onto curves of genus greater than 1. So if C prime has a genus greater than 1, then there is almost no chance for other curve to map. First, C has to have, for a given curve, almost no chance. Certainly there are curves which map, but it is a very small subset. Okay. So therefore, and similarly, if you're looking on the covering, it looks like it should be very rare. However, I will say now, I will tell immediately what I think happening. But it is kind of conjecture, and I will be moving towards it as close to it as possible. And I will say where is the boundary of our understanding. So conjecture is important. Any curve C defined over Q bar G of C greater or greater or equal to dominates any curve over Q bar. So that means if you take, so now we are restricting ourselves, yes? So we take this countable subset, and I'm looking only at countable subset of curves. If the curve is defined over Q bar, then it's unramified coverings are defined over Q bar, so it's kind of closed under this operation. The subset is closed under it. And then the conjecture says that in fact any curve, so that all the curves are essentially the same. So modally unramified covering, strangely enough, curves of genus greater than 2 should be kind of similar. And on a complex level, we saw this similarity, namely they all have the same covering, yes, so they all have the same covering. But this is on algebraic level, which is completely different. I must say, I want to stress the difference. So in fact, what these statements, this conjecture says that in fact there is an algebraic version of H. There is something, some object, so-called pro-algebraic object, which covers it. Nature. Okay. How can we get there? So first result in this direction, and that was actually what inspired the whole thing. Okay. Was a theorem of Bely.
Excuse me.
Yes.
Excuse me. C tilde in this conjecture, C tilde will be defined. So if you say that C any curve dominates any other.
Yeah.
Okay. So you should have this diagram that you have on the left.
Yeah.
Okay. And C tilde will be defined where?
C tilde is also, so you take, C tilde is also algebraic. It's algebraic. So algebraic, the set of algebraic curves is closed undertaken under quite curve. Yeah, so it kind of there are many operations which work on this countable set. Huge, as I pointed out, this huge countable set, dense countable set. Yes, but countable is still countable. So you see, countable is still in some way look like integer. And that's what I'm going to say first, that there is a set. So there is not one curve, but a set of curves which looks like z, parameterized by z, which dominate it. Not one, but okay, so I'll formulate exactly. So maybe now I formulate here. Let Cn be a curve defined. Maybe I'll define it by a question, xn minus 1. So that means we take, so essentially it is C, so maybe I would say C of Cn over C of x, yes, is equal to 2. So this is a very special class of so-called hyperelliptic curves. And you can say, so hyperelliptic curves usually are obtained as, it's also covering of P1 of a sphere. So you these two choose last 2 points. And here these points are very particular. These are roots of unity, plus unity. Okay. So this is very particular class of curves. Yes, and then and therefore what we are getting is so what I call, so let's see and be this class and then the theorem for any curve C prime defined over Q bar. There is n, a number such that Cn dominates C. So we have now a small class of curves, one for each genus. Yes, we select one hyperelliptic curve for each genus, so that for any C prime, the one of these curves dominate. Okay. The proof is based on so-called Bely theorems, which I formulate now and give a sketch of it. Okay. So the theorem, Bely theorem, which was proved in 1978, and which has a big strange story, is the following, that if the curve C so is defined over Q bar, if and only if there is a function f to Q1 which is Unramified over 0, 1, infinity. If and only if. So that means ramified means what? So you have a map. So F is a meromorphic map. So locally you can think about it. So locally in coordinates, near every coordinate, so near every point P in C, you have a coordinate Z, and then we have a map. Our map looks like, let's say, parameter U here. U is a parameter here, parameter. And then we have a map, U equals Z to the power M. And if M is at almost everywhere, M is equal to 1. That is a unramified. Almost all points are unramified. And if it is equal to M, if M is greater than 1, yes, then we call P a ramification point. and M ramification index. So in particular, what means this statement? That means we have a collection, so for any f, we have a collection, a finite collection of ramification points. Pi, and f of the union pi lies in 0, 1. You see, the interesting point is the following. So suppose we want only 2 points. So suppose that all ramification points map in 2 points. Then immediately our covering is very restricted. It just be 1. So if I would say, okay, all ramification points map into 0 and 1. Then our covering becomes just a map P1 to P1. Let's say here parameter U is equal to 0 globally. So parameter, we have a parameter, one parameter here. So for some parameter, we will adjust this map, nothing else. However, if you ask what happens when we add ramification 3 points, then first thing what happens is that you can, basically, you immediately get all possible curves. So if the curve is over Q bar, then it has such a function. If not, then it is not. Yeah. So adding more points in some more, let's say, Q bar points in ramification doesn't add anything. Okay. So, in fact, this problem, what are the covering with 3 ramifications, was considered in connection with so-called inverse Galois problem. So finding extensions of rational numbers or slightly bigger fields with a given Galois. Okay. So, however, in the process, this theorem was proved as a byproduct. The theorem was not a target. At no moment in history, this theorem was conjectured, or even nobody ever conjectured such a statement that nobody would believe that it is true. Because you see what happens here. So from the outside, because you see what happens here is that you have a pure arithmetic property in terms of complex coordinates. This property is purely complex. Okay. Having a function with map is given ramification points, it's all formulated for just complex curves. Yeah? For formula 2. But however, this strange property happened to be identical to curve being arithmetic. Okay, so now I want to get a digest of that's the initial proof of Bely. There were some. So what was so we're building such. So let's assume that C is defined over Q bar. Then it is equivalent to the following simple statement. I won't even explain why. It is quite clear that there is a function. So if you have an element, so here, that means here inside C of C, there is Q bar of C, and hence if you take element from here, so if you take element from here, then its ramifications, so F defines a map C to P1, and then df equals 0 is equal to ramification subset. So ramification subset is actually can be defined in terms of differential. Differential equal to 0 of f, local. we have local coordinate, get local differential, then this will be a union. So the property, so now if we take the image, you see if f is here, then df is also kind of over Q1. Like it is true on P1, and therefore it will be true everywhere. It's a local property. So something which is defined over Q bar has a differential also defined over Q bar. So therefore, f of df equal to 0. The set will be inside Q bar. Is in Q1. So it's a subset of Q bar points, but maybe I would say Q1 Q1. So it's a subset of, so the image of these points, of the ramifications, is a set of algebraic points. The image of algebraic points and the map defined over algebraic numbers are again algebraic numbers. Okay, and that's the only thing we need. So we can start. So the building, actually, what I'm going to discuss is not a proof but an algorithm. So what I'm going to say now, that I will so from the map, so we have a map F, and then I will add two more maps, F0 and F1. So that the composition has this property. So my map, so map 3-point map, yes. So okay, I have F over there. Okay, so this composition H will have a property that H of GH equals 0 is contained in 0, 1. So and that's important, that you can see that if there is one such map, there are infinite domains. So you actually can build such maps if it's plenty. Okay, so how to, so these two steps are, okay, so I'll write this, sorry. Sure. Okay, so these steps, the steps are the following. So first step is, so let's say, so we can view, so P1, so C maps to P1, and now inside P1, so we can view it as Q bar plus infinity. So what is P1? After all, P1 over Q bar. So points are Q bar and infinity. And now we have a map, so we have F over df inside Q bar. Yes. So this is a finite set. Let's say defined over Q bar. And we can assume by moving by infinity is not here. So assume infinity is not present. So we just can, let's say we always can apply some rational projective transformation, so we can always assume that. Now, what means that they are over Q bar? There is a polynomial. So you have n points over Q bar. So there is a polynomial f phi 0 of x1, xn. So it's of minimal degree. Such that this is contained in Q. That this, okay, that, yes, that this is equal to 0. Let's say that. So we can collect, there is a polynomial which deals with this, and assume that the degree P0 is n. Then, so now we have a map, so in a way that will be, so now we will be building F0 And it is the first step in building, let's say. Yes. Okay, that's the first one. So F0 will be also a product. And I want to say that it will be exactly a product of at most n0 maps. Namely, you see, we are looking at ramification points. It means we take dp0 equals to 0. Yes. Now, the polynomial, and this is a crucial statement, degree of differential of dp0, which is, let's say, dp0 by du, which is parameter inside here. So this is here. This is a linear line inside Q. There is a parameter, and so we take dp0 and simply take the derivative. P0 is polynomial of degree n0, so therefore this polynomial has degree n0 also. We take polynomial, take derivative, it has degree n minus 1. It is also defined over Q. We take polynomial, yes, over rational polynomial. And now, therefore, we are getting the subset defined over Q, but degree of this subset over Q is small. Yeah? So, therefore, we can take phi 1 such that maps dp0 p0 of dp0 equal to 0, and degree of p1 is less or equal to 0. Now what happens? This is polynomial. Yes. So whatever happened to the previous coordinates, they are already rational. So 0 is rational point. So this image, this dp0 is rational. So therefore, the image phi 1 maps all dp1, phi 1 of phi 1 maps dp0 plus 0, p0 dp0 plus 0 into rational numbers, into 0 and a rational number, and we can proceed. So this polynomial has degree n0 minus 1. Take the image of dp1, p1 of dp1 has degree less than n0 minus 2, and so on. So each time, what we are doing, we diminish the degree of the subset over Q. So that means at the end we are getting many points. So here we have P1, P2, and so on. And then in n and at most, we can actually make some we can remove rational points. For example, if rational points occur already in the image, we can remove it. We just can keep track of points which have bigger degree in the image. So therefore, at the end, we obtain a map 2P1. So this composition has only rational images of ramification. So this is, let's say, H0, yes? So H0, what we achieved, we have a map from C to P1, and all ramification points of this map are rational. Now, the next step, so this step is very, maybe I won't talk about it, is not very particular for the problem, so here the field is not, we can do it for other fields. I would say that, I would just make a how I would tell that, this is a way also using the same trick. What we can do, we gave this quantitative very short group desingularization symbol. So there is a half-page proof of the famous result similar to hierarchical result, the existence of non-singular models in complex case. Using this trick, it's kind of immediate. Next step, however, is very much depending on the fact that we say rational. Rational is really Q in rational number. So, you know, rational has many different meanings in algebraic terms. And rational section or rational variety, however, this is here the rational is rational number, and namely, now what I'm going to use, I'm going to use a very particular functions. There exists this kind of function. So let's take this polynomial. This particular polynomial, and that was Bely discovered this polynomial, it makes the following. It takes 4 points, 4 rational points, 0, a plus b. It maps them. I think it's correct. Maybe I have to put some coefficient. Okay, put lambda. So I want to map into 0, 1, and 2. Yes. And just in order to adjust to make this to 1. And also its ramification. Ramification. Its ramification. So let's say f a b. So df of b equal to 0. Differential to 0 is contained in this set of points. So we have a polynomial with the following property. With the following particular property for these 4 points. It takes these 4 rational points, map them into 3 rational points, because 0 and 1 are mapped into the same point, into 0. And at the same time, it has a very small ramification. So its ramification, its differential is trivial, certainly. I would say it has ramification at infinity, 0, a minus 1, infinity, 1, because of this, and one extra point. But this extra point is mapping. So this collection, this is kind of conjecturing function. So now what we do, next step, as I promised, I erased this. So next step is building F1. Yes. And next step, building N1, pick up, so basically have a collection S, collection of rational points coming from images of ramifications of DH0, yes. And pick up 4 points, so S, pick up any 4 points, 4 points in S, and then apply G, let's say P1, P2, P3, P4, yes. Apply G in PJ to Q. So take a basically rational projective transformation of P1 such that G of P1, P0, P1, P2, P3 will be mapped, and it is easy to see that it's possible. 0, infinity, 8 by 8 of P, yes? For some integer numbers. So important thing, here is the most important thing, that, you know, these numbers which have degrees are also provide you with a coordinates for rational number. And then apply, and 3 apply for some. So for some A, B. Okay? Some algebra. Some integer numbers apply F, C, B. So as a result, we obtain from S the set of S minus 1 correction. And we didn't increase the So we just so therefore, if we have S point in S minus 3 steps, in S minus 3 standard steps, we obtain this map. We obtain that H. Okay. So that's a proof. The opposite direction is kind of trivial and was well known. That if you have something ramified only on all points like 0, 1, infinity, or any 3 points, because any 3 points can be moved into 0, 1, infinity, then this curve defined as a proof. It was kind of understood, but this direction, that was completely kind of unthought of. Okay, now in the last minutes I will say how does it imply that theorem. The theorem, dominance theorem for Qian, and then briefly say what is known. Okay. So, so how does it imply? So let's take a curve of QR. So let's take C prime over QR, and consider Bely map. H, yes, 2Q1, and its ramification indexes all ramification indices. Mi of H. Now I want to take a number which is divisible by all this n. Take n such that it divides, is divisible by all n. And then take, so now we have a map y. Yes, so Cn, I recall it's y squared equal to xn minus 1. Maybe I'll put 2n. Let's put 2n. Just for sake, I'll explain it. So take 2C2n, which is, and this has map y, yes? This map has degree 2n, and its ramification points are exactly 3 points. Please check. Because in other direction, you just look at other direction, it's quadratic. So therefore, you will have x, you can say y squared minus x to the 2 power n, and therefore it will be degree 2n, and ramification points are 0, 1, infinity, and here is 2n, and here is n, or also 2n. It depends. It's n. So that means there is a 1 point, so this curve has 1 point over 0, with huge ramification to n, here to n, and here 2 points with ramification. Okay, an example is, for example, the curve C3 is just like, it's odd, so it has 3 ramification points. This is famous elliptic curve, which maps with degree 3 on Q1. Cyclic curve in Greek. Okay, so now, and then I want to take, you see there is a standard procedure of taking so-called product over Q1. Basically we have 2 maps, C2n onto P1, C prime onto P1, yes? And there is a diagonal. So we take product, and then preimage of diagonal. So since it is diagonal here, the preimage will be again a curve. And in this case, we can check that it's in fact just a curve, So this is C2n. And the claim is that it is a claim. The combination map here is unramified, this arrow is not. And the reason is so-called Abinkarem, which everybody can prove by himself. In order to see, so what is we have to look at the local picture. So suppose we have a point P here, and let's say, so we have to look at P is pre-image of point here, so we have a disk here, dz, inside C to N, and we keep Z prime inside C. So that U is locally, this local coordinate is equal Z to N, yes, so this is, so Z P here, P prime here. This is a ramification point. We only have to look at, if the point is non-ramified, it is non-ramified, nothing happens. But if we have ramification points, degree N here, and degree Ni here, then we have a local map, U equals Zn, okay, Zn, and P prime is U is equal Z1 Ni. Okay, so what is a product? So now we have a map to a disk, U, and so now we have D1, dz, and D2, and what is a product? So you see the product is, the product over disk will be a bunch of disks. So that means when we take a product, that means we have, here we take, here coordinate is root on N of U, and now we want to adjoin coordinate root Ni of U. But you see, if you have root N of U, then root Ni also is a function. So therefore, the map here is a collection of plane disks. If you take a root, suppose you take a fourth root of Z, and then and it exists already on your surface, and then you take N, second root of Z, then this is 2 copies. So therefore, in that direction it's just a bunch of copies, and then in this direction it is some map. But the fact that it is a bunch of flat copies means that this map is not ramified. In particular, therefore what I proved here, if we have a map on C where all ramification indexes divide N, then this curve C to N dominates. So basically, in that particular case, C to N dominates. Okay. So in this way we have a set of curves which dominates everything. But this set is still very big, so I will take. So later on, I must say this kind of topic came out of this conversation with Martin. He actually pointed out that you can do it for modular curves. But then for many years there is no progress, but now there is some. And I want to say that what we can prove, so if now we can work with just Cn curve, and what we can prove that basically any Cn dominates C6. C6 in turn dominates any C2S, say K1, 5T. Yes, and then, so in particular domination among this curve depends very much on a divisibility. So this is kind of smallest curve. The smallest curve dominates here, and moreover this curve is smallest in the following sense. R tilde R dominates C if R is any hyperelliptic. And there are many more results in this direction. So the problem here is 7. So for example, we don't know if C6 dominates C7. However, so therefore, it's a question mostly about prime numbers. Which primes dominate which? And which products? So there is a kind of very non-trivial relation between numbers, which Cn dominates which. And in our, so this was joint work recently, I worked on it with, so we started it with Yuri Tschinkel. I'm with Yuri Tschinkel for series. It was beginning with something like that, and then many other results around this. And then recently with Qian, we proved, but by building some very particular polynomials, and that's why I like to talk about it, that there are many other, like C6, C13 dominant C7, C6, 1143 dominates C7, and so on. So there are some results like that, but this is given by rational functions constructed for the ratios of polynomials of degree many millions, and we couldn't do that. So at the moment the problem is how to. And there are some. So if you want to see details, you can look at our articles with Qian. I think this is now on the internet, and also some related article. I didn't say anything about elliptic curves, starting points of elliptic curve, but elliptic curves play a significant role in building huge families of dominating curves. So maybe for a colloquial term that's quite enough. So whoever wants to look at it, I think this is an interesting question, and there are many questions inside this theory. What will come up, I don't know. I still hope that let's say prime numbers are connected. That means every curve dominates every other curve. But maybe there are some dividers, and we can get from some of these. Okay, thank you for attention.
What happens if we ask some similar questions in higher dimension? For example, all these techniques cannot work, but we can already ask this relation of being dominated.
Yes.
If it makes sense for all.
You see, the question is in general, what are dominant classes? So currently, we just put an article with my student Fedor Bogomolov, where we are trying to prove that some kind of smooth vibration of smooth curves are dominating everything. You see, many questions about, let's say, exactly arithmetic of algebraic variety, they can be lifted to everything what it subjects. So therefore, the dominance here, this kind of dominance is particularly nice because it's unramified. Ramifications of that bad, but there are some questions which are kind of related in high dimensions. Though the whole theory, as usual, as I said, projective geometry in dimension 1 is perfect. That means usually the higher dimensional geometry is attempting to imitate one dimension. And it can do it up to some extent, but usually it's getting much more difficult. So therefore in higher dimensions, it's getting more murky, I would say, to put a straightforward generalization. There were some attempts, like Paranjab and some others were making attempts to do it. But it's not so easy to make them, though there are questions. You know, nobody knows, for example, maybe, and we discussed it with Gromov a long time ago, don't think there is any progress, but maybe any variety of a Q-bar is dominated by the Volkov. Even that is not known. So what lies on top of everything? We know that projective space lies below everything, every projective variety, but what is above everything?
Yes. What we said before. You mentioned the fact that at the beginning you spoke about the moduli space.
Yes.
So in one sense, during your talk, you were always saying that there is something arithmetic problem. But on the back, there is this fact that the moduli space is really a good moduli space.
Yeah.
Does it have an action on all your work, or because we?
No,
Because
You know, not much.
in an unstructured case, because it's, the modular space is smooth and you have a lot of good.
Not enough.
Not enough.
Many good, but not enough.
Not enough.
Not enough to help with this problem. This program, how to say, as usual, how to say, this the question here, but it's a standard situation on algebraic geometry that many questions depend on very delicate, very particular construction. Like the group of Bely theorem depends exactly on the existence of some type of strange plane. Yes, and so there is something kind of, you need something very specific. And maybe you can build something, if you find something interesting, let's say map or something, maybe you can build the whole thing. But, okay.
Not just enough.
Not just enough. No. It's kind of question goes some different directions.
Do we have any other question? Please.
So you said that you take the question of dominance between two curves C and Cn is incorrect. That's the problem in number theory of the relation between M and N. So do we have some conjectures in this direction? For example, that if M and N satisfy some sort of relation?
Look, if M and N, if M divides N, then Cn dominates Cn. By the same, yes. So there are such things, but not many. You know, all these constructions, you see the numbers, yeah? What I mentioned here, like that. The construction, it just kind of building, using elliptic curve, you build some tower of maps, and then all of a sudden you're getting small indices. So in a way, what you can say that if you have, so this number you can add to any n. So if you take n here, and n add n here, then you will have, I think you will have something. So something like that you can. But what's going further, there are some arguments, maybe you should look at really our article. There are some particular arguments, and maybe I would really, why I'm talking about usually, I like to talk about it because I want people who have some computer skills to get it. Because maybe it's just a question of a good program. Because you can build something, so with Qian we wrote some kind of potential contraction algorithm, but it depends on the calculations. So that means maybe you can take some kind of a number of integer numbers and then find a good map which maps it together with additional ramification points to a smaller number. So we have some kind of generator, but it needs to look at kind of algorithm. It's usually, maybe there is a way to at least build maybe infinite program, but which will slowly, in an infinite time, cover up also.